So, I mean, everything that if you understand what the parent function of a quadratic looks right? And if you understand this, everything you've already done transformations, right? So you know that it's going to have this parabolic curve, right? It's going to be going something like this. If this is y, this is x. It always has this shape, could flip, right? Negative, etc. So that's kind of something you've been working with so far. Something I haven't emphasized in a class, because I do this more in Algebra 1, is the reason for the shape, and I have a hard time drawing nice even curves on my whiteboard, but it's because of the way that it grows. When you think about, let's just say take the straight line, right? If I have, a straight line, the slope of that line, it has a constant rate of change. This would be, say, a 45-degree angle. Any direction that if I go up any number, I could go over that same number, right? I could have this little stair step thingy going, and that's going to be my rate of change. And that's how it grows. It just grows in a linear fashion. It's a simple ratio, right? And of course, if it's steeper, it's going to be greater than 1. If it's flatter, it's less than 1, and so on. But when it comes to if you think about how the quadratic grows, well, it grows by squares, right? If I go over 1, I'm going to go up the square of 1. If I go over 2, I'm going to go up the square of 2. It's going to go up 4. If I go over 3, it's going to go up the square of 3. It's going to go up to 9, and so on. Okay, my scale's not exactly right there, but that's how quadratics grow, right? I mean, I probably should have put this on Desmos so you can really see it, right? And if you so everything is going to be relative to that. And in fact, that's probably not a bad idea. When I teach this in algebra, I always spend some time on Desmos, just kind of let's explore, like, what does it look like? And if I do this, if I do that, this kind of understanding, that if I have, y is equal to x squared, it's not y minus, should be equals, right? If I have, you could see it, right? That everything here, the way it grows by my squares, over 1, up 1, over 2, up 4. You could graph any parabola this way, right? You don't actually have to do plugging in points, okay? It's not just a shape. The shape is determined by the way that it grows, right? If I go over 3, the next point up is going to be a 9, and so on. And this is where you start, if you're understanding this, this is where you start to understand, well, what would happen if I double it? Well, it's going to grow by twice the square, right? And just kind of, again, understanding this goes a long ways. So if I go over 1, I'm going to go up. If I go over 1, I have to go up 1 times 2. I go up to 2. If I go over 2, I go up 2 times 4. The next one I'm going to hit is going to be 8. It's going to be way up here. So obviously it's going to grow a lot faster. That's what we call it a stretch factor. It's because it stretches it up because it makes it grow twice as fast, right?
Does that mean you have to say it stretches vertically?
Yeah, because notice again, the stretching vertically, it's like I took the two ends, right, and pulled them up. And that's how I end up with this parabola here, right? So you could imagine if you had a weight down at the bottom of, two things that are hanging, right? If the weight were heavier, right, it would stretch it vertically. This is why these are used in physics, because there's a lot of physical applications to this.
So is a stretch on the horizontal, that's with the fractions?
Yeah, that's essentially, yeah, if I say I'm going to, we also actually might call it a vertical compression. Watch, I'm going to make that point too. Okay. All right. So if you notice, we wouldn't say it's stretch. Oftentimes we'll say it's compressed. It's like we've squashed it down. So actually, a horizontal stretch is really kind of the same as a vertical compression. Does that make sense? They're really the same thing. There's a slight little nuance in terms of how some people might define them differently. But if I squash something down, if I compress something down, right, then it's going to flatten it out. It's going to stretch it out over the x-axis. So that's kind of where these start to have a little bit more meaning, you're going to find is when we're going to start working with, I'm going to show you just kind of where we're going with this. If y is equal to the sine of x, okay? And what you were going to, so I'm going to, and so if y is equal to twice the sine of x, right? You start to see, like, do you notice here, this is no longer, it is literally vertical. Do you see how we're going to be doing this in January, February, that the blue one is vertically stretched. Do you notice how all the zeros are the same? Do you see so we literally are pulling it up and down vertically. So we're going to,
I'm a little confused.
I just moved, you look down, I think when I put those in. This is another function. This is a trig function you're going to be working with. Same thing applies though. What did I do? Okay. First this is my graph of sine of x. You'll know exactly why this is the case in January. Just take a look at the graph. It's a wave. Okay. This is
Like
why
a lot of parabolas.
but you could, I guess but they're not going to grow at the same rate as a parabola. They have their own growth rate. In other words, I don't go over one and up one to get to the next point. Do you see that? So these are going to be trig weight. You'll see this is going to be related to the circle. You'll know exactly what this is in January. What I wanted to show you is it doesn't matter what the function is. Okay. By the way, did you notice there was a pi in there?
Yeah, that worried me a little.
Well, that's because it'll make sense. It's related to a circle. Okay. But notice what happens if I put y is equal to twice the sine of x. It just doubles the height. Do you see that? All it does is it vertically stretches it, right, from one to the other. So what you're learning about vertical stretching and all this stuff, this is just related to, this is going to be true for any and all functions. If I draw a log function and do twice, right, it's going to raise the height or lower, you know what I mean? It's going to stretch y vertically, okay? And this is where, again, you can get to where you can predict things. It's a principle. Look what happens if I say y is equal to the sine of twice x. Well, that's compressing it. So there is a difference between stretching and compressing, okay? In other words, I'm shoving two waves in what used to be only one, right? So
Wait, wouldn't you want to compress it by dividing it by 2 instead?
well, that's another way to there's more than one way to compress it. This is actually going to have to do everything to do with sound waves, light waves, right? You can slow down the wave. That would be what you're talking about. Watch. This is going to have an implication of sound. So this would, like, if you think about if this is a sound wave, this would be a softer sound wave, but it would have the same frequency. This is where the physics, it's going to be very cool. It's going to explain all kinds of physics. So this would be, when you talk about amplifying sound, this is literally what they're talking about. Amplification is how high or low the wave is. That's how loud it is. Okay, but the frequency might be, whether it's high, low, right? The more it's bouncing back and forth, that's going to be frequency, and that's what's going to be affected by this. What if I'm going to put 5 in there. So this would be half as loud, but 5 times the frequency would be up by a factor of 5. So
it would be quieter, but it would sound different.
It would sound higher. Higher frequencies have a higher sound on our eardrums, right? So higher frequency sounds. So do you understand the stuff we're doing with parabolas? It's going to be related to all of these, okay? If I did the log of x, and then I do y is equal to twice the log of x. Okay, again, do you see how I'm stretching it vertically? So you're going to be able to predict kind of what's happening. And if you understand what the graph represents in terms of X's and Y's, it helps you predict what would be happening in the real life instance that we're using that for. So we've only been doing these with parabolas, right? But the same principles are going to apply. So if you notice, in this particular case, right, if I do stretch it, right, then it does create this little stretch look, which looks like it's compressing it horizontally, but that's because I only have a y squared. It's a simple function. But I have more complex functions coming where compressing it doesn't necessarily mean the same as stretching or shrinking it, okay? So this is doing something to the function, right? Here's a good example. What if I did y is equal to x to 2x in parentheses squared? Okay, so that's going to be different. I would prefer that to be a different color. I don't know why they did yellow again or red again. Usually I can try to get that color to change, but oh well. I'm going to move that one back. Okay, so here's the difference here. Do you notice how doing twice x, that is actually compressing it on the x-axis? Do you see what I'm saying? Whereas if I put, let's just say I do half x, that's going to bowl it out. Okay, so that if it's
The
inside
compression is
parentheses,
throwing me off.
huh?
The compression is kind of confusing me since
It doesn't really, compression doesn't really apply much to parabolas. It applies more to the waves. But you can see that it's almost like I've squashed down the bowl. Do you understand? That's kind of what I'm looking at here. The red graph, it's as if it had been squashed down. Do you understand what I'm saying? So to me, if I could imagine that, these graphs ended here. Do you see what I'm saying? What if I just said, I'm going to put a little line in here, actually. I'm going to say y equals, I'm going to do, say y equals 8, right? What if I cut it off here? If you notice, it'd be like this is a squashed down bowl version of the first bowl, right? Okay. So that's the idea of compression. It's as if I pushed it down and made it flatter, right? Okay. But it will make more sense when we're dealing with waves. The waves are actually the easiest ones to understand because you could think about compressing a wave or stretching it out. Compressing it vertically would be like take a slinky, right? And then you put it back to, so a slinky is a great way to visualize waves, right? Okay.
got it.
Okay.
I
So
think.
anyway, these are the principles that you're learning here. I don't worry a lot with parabolas about compression or but compression, but if you or how shrinkage, all that kind of stuff, because it doesn't really apply. But you can see vertical stretching and you can see vertical, what's the opposite? Compression, right? And that's usually what we're going to see in terms of this version here. Why this is why I pretty much focus on the coefficient in front of the x squared is really what's going to have that most effect. So the bottom line is, and again, I'm going to make this a half, right? If you notice, if you look at the way this is growing, okay, right? If I were to think about how does it grow, well, and this is the same thing as slope, right? Over, up, or up, over. But as I put in, the original one, if I put in an X, if I put in a 1, I get, well, these are, I don't have my original on here, do I? I'm going to have to put it back on here. Y equals X squared, right? Okay, there we go. That'll be purple now. So when you look at your original one, that if that's the purple, I might as well make that purple. Right? The purple one, that if I go over 1, I go up 1, and that's like the normal parent graph. Okay. If I compress it, which is the green graph, I'm doing half. Okay. Right. Well, what should happen is I go over 1, I go up to a half. Notice that's what happens. I go over 1, I'm I'm there at a half. If I go over 2, I should go up half of the square of 2. I should go up to half of 4. And notice that's where I end up, right there. And so if I go over 3, I should go up to 4.5, half of 9. And I do. You notice there's 4.5. Okay. So that's how these things grow. They grow by the squares of their inputs. And then from there, you're looking at, your translations of, are you shifting it forward, backwards, up, down? Are you reflecting it? All of those things help you understand, the picture. Okay. So the more you work with the picture, the more the algebra starts to make sense. And I'm going to bring up a few things about the algebra, right? We know that even if I move this, so I'm going to call this, I'm going to say x minus 4. And that's going to be squared, what should that, if I do this, what would it be?
A parabola shifted over 4 to the right.
To the right. So this one, I've shifted it over. Oh, and why not? Let's shift it up a couple units too. Now I'm going to shift it down because I want some zeros. There we go.
This function isn't odd or even, right? Because it's not symmetrical.
Exactly. It's not symmetrical to anything. Exactly. So yeah, that's the nice thing. The graphs are really easy to see them. They have to be symmetrical, right? But you do notice if you put an input, you can already see the -2 will always be the same, but this is going to change depending on whether this is positive or negative. So you're going to get a different result. You don't even have to calculate it. You'll know it's neither. So, but let's think about it. What's my anatomy? Well, this is going to be symmetrical, right, to this line, right? Everything on this parabola, the vertex is the only place that it has the 1 point, but everything is a plus and a minus, right? Okay. So if you notice, these are going to be, we call these what? Solutions. So they have 4 names. They could be called solutions. They can be called roots. They could be called zeros, and they could be called x-intercepts. These are all the same thing. Okay. The thing about roots and solutions is once we have complex numbers, they can also occur on the complex plane. They wouldn't show up on the x-intercept, but in the real number plane, all 4 of these mean exactly the same thing. Okay, so there's a reason they've been called zeros. So when you think about this, is where what you've learned in algebra begins to make a lot more sense. Take a look at, let's just say I factor. Now these don't have integer roots, so what would I do okay, I know. I'm gonna change this one more time. I'm gonna make it have integer roots, and it'll have integer roots if I'm subtracting a square. So let's just, do you see why? Because do you see how I do that?
Because it's difference of 2 squares?
Kind of. If I set this equal to 0, I'm going to get x minus 4, the quantity squared, is equal to 4. In order to get this isolated, I have to take the square root of both sides. So if I'm subtracting the square number, I'm going to get an integer. You see why? Because I'm going to take the square root of that. So I'm going to get x minus 4 is equal to 2. Therefore, x is plus or minus. X is either equal to 4 plus 2 or x is equal to 4 minus 2. And notice, this is the x equals 4 line. This is my plus 2. This is my minus 2. The graph is going to exactly match my algebra. Do you see that?
Yeah.
Yeah. Okay. So this whole thing about taking a plus or minus, it's literally the line of symmetry with the one root, the line of symmetry with going this direction, going that direction, just reflects the symmetry of the graph. And the only time this won't happen is if the vertex is right on the x-axis, which would mean this is a plus or minus 0. And you'll see that's why, because I don't have a plus or minus. I'm just going to have one solution. Okay. So when you understand this, and you understand how it affects the picture, right? You get it all. And I'm actually gonna I'm going to put that line of symmetry in there. It's very helpful to see it. And I'm going to zoom out or zoom in a little bit, drag it over. Okay. So again, so there's always two things we're concerned about when it comes to a parabola. I thought that we never care about anything else, but 90 some odd % of the time, what we care about is this or this. Okay. And in fact, I'm going to do one more thing. I'm going to flip this upside down because one of the most understandable versions of this is a projectile motion situation, right? Okay. And if you have, let's see, if I drag that, that's fine, right? So if you have projectile motion, I'm going to make it even. Oh, yeah, I think I'll do that. I'm going to do this. That way I get there, that's perfect. Literally, 16 is a.
That is a big parabola.
Yeah, well, all I did is, there we go. My scale is kind of off here. Let's just do 20 by 20. There we go. Make it look a little bit more like a parabola, still more than I need. You think about projectile motion, right? To me, this is one of the easiest ways to understand what's going on with a parabola, with quadratics, okay? In this case, this would be like, hey, I start here. If I throw something up in the air, gravity is going to pull. I give it this upward thrust. Gravity pulls on it, keeps pulling on it, right? Even though I've only given it a force up once. So that's why you get this curve. It increases, but at a decreasing rate until it hits the point where there's no more momentum left, right? And then gravity starts to pull it back down. And in the real world, we would end right here, right? We can't have negative unless there's a hole where it lands, then maybe it can go a little bit further down, right? But this would be like I can maybe kick a ball straight up in the air and it lands back down on the ground. So that's kind of what we're doing. And when we want to know the top height, well, the top height is the vertex, right? It's the maximum value. And that's why very often, we're looking for that maximization or that minimization. We want the vertex. And so if we're going to take that maximum value, that's one of the tools that you're going to be using in 3.1. What we're going to do, we know that this line of symmetry here, right, this x equals something, is going to equal negative b over 2a. Okay, you do have to memorize this. This is actually the first part of the quadratic formula, if you haven't noticed it. Okay, the quadratic formula, which you have memorized, right?
Yeah.
Equals negative b
Plus or minus the square root of b squared minus 4ac all over 2a.
And I like to write it this way because if you notice, this is the line of symmetry. Here's that plus or minus. So here's my line of symmetry. This is my plus quantity. This is my minus quantity. That's what the second part is. This part here is over here. And this part, the plus goes this way, the minus goes this way. Okay. So actually, there's this really weird relationship between the quadratic formula. I'm going to write it over here. Okay. That if I take what's under that root, my b squared minus 4ac, if I make that negative, and if I double the denominator, I'm actually going to get the y coordinate. If you actually do use the quadratic formula, it'll give you this is actually in the notes, and I'll probably bring this up again in class, but the traditional way that you can find your maximum value is first you compute this here, and then you plug that in to your function. Now, this function is not in that form. It's not in the ABC form. I can't call it standard form anymore because now standard form has different meaning here, but I could take my y equals negative x minus 4, the quantity squared. I could rearrange this, That's going to be y is equal to, if I square this, I get negative, I'm going to do negative x squared minus 8x plus 16 plus 16. Oh, okay. That means I'm going to get y is equal to negative x squared plus 8x minus 16 plus 16 is just going to leave me this, right? And that should
Would you
make
want to
sense.
keep factoring that?
Huh? I don't want, I want I want to get my A and my B. So I don't want factored form for this. If I did, notice I'd get my zeros. Y is equal to what?
Uh, negative x times x plus 8.
Yep. And what are my zeros? 0 and 8, right? If I set this equal to 0, what values will make it true? My 0 and my 8. Okay, but it still doesn't tell me this value. It doesn't tell me the 16. And usually if you have the if you have this, if you're not, so factoring would give you zeros. And maybe I want those. Maybe I want, if anytime they say I want solutions, they mean zeros. Zeros and solutions mean the same thing. Okay. But if I want the maximum value, really what I want is I want the y value of the vertex. Okay. Now I'm going through a lot of work to give you what's already here because this is in vertex form, right? But if you have this, what used to be called the standard form, really hate that. What I do know is that A is equal to -1 and B is equal to 8, right? So I can plug it in here. And what am I going to get? I'm going to get -8 over -2, which would be +4. So if I plug a 4 in here, what am I going to get? I'm going to get -16 plus 8 times 4, 32 equals, there's my 16 right there. Okay. So anytime I have this, the algebra 1 used to be called standard form, the one that's in ax squared plus bx plus c. I don't even know what the book calls this now, since they called this the standard form, right? You would, to get a max or a min, you'd use the negative b over 2a, okay? And if you think about this from projectile motion again, what does that tell you? If this is time and this is the height, okay, right? Well, it tells me, let's just say it's in feet, okay? It tells me the highest this object went was
Miss
6,
Julie,
yeah,
if I understand correctly, you're saying we find the x value using the negative b over 2a,
yep,
and then we plug whatever the solution is into the negative b
yep,
squared, and
exactly,
then that's our x coordinate
yep,
and our y coordinate?
yeah, the whole vertex. If you don't have this form, and a lot of times it's not convenient to get that form, I'll work one from start to finish on the whiteboard in a sec, okay?
Thank
I'm
you.
just, I'm just talking about what do you get from that? Well, if this is a real life example of, say, height and time, I would know that it took, say, 4 seconds to get 16 feet high, which doesn't make a whole lot of sense the way it'd have to be maybe it's a balloon. I don't know, something really light, right? That has some air friction. Okay, so
We're just throwing really hard.
yeah, that doesn't really make sense in terms of the context, but that's what it would mean. Okay, so what I'm going to do is I'm going to go over to a whiteboard. I'm going to work one of these from start to finish. Okay, if I can find my whiteboard here, which is here. Okay, all right. So we're going to work one of these problems. This is in the homework. Okay, this is number, well, actually, do you have your book open?
Yeah.
Okay. If you take a, let's talk a few conceptual ones. This is number 4. This is in 3.1, of course. Okay. On page 229, 230. Number 4, it says, right, if you're given that the f of x is equal to -2 x minus 3 squared plus 5. Okay, what does that tell me?
The graph is shifted up 5, over to the right 3,
Yep.
and it's flipped
Yeah,
and stretched vertically by 2.
exactly. You have 4 transformations here. Exactly. So I've taken this parabola. You could look. I usually look at this first. So I've flipped. I reflected it across the x-axis. Right. That's flipping it like this. Okay. That should be 2 s's. And then you could say either one of these shifts, it doesn't matter, right? I would actually do the vertical stretching first. This would be, it's gone up 5, it's gone over 3, right? I've shifted that. And then the vertical stretching, that would be keep the vertex where it is, but it's gonna be skinnier, right? So if you were to sketch it, right, you'd know, first of all, where would the vertex be?
5,
Vertex
0, 5.
So the vertex would be at 3, 5. 3, 5. This is remember the H and the K?
Oh, yeah.
Yeah. Okay. So I have it anchored here, and then it's going to grow at twice squares upside down, right? So that's kind of what we know based on. If you were asked for what's the maximum value of the function, how would you answer the question?
You'd you'd have the y coordinate and put at x value of
If they just ask for the maximum value, it's just 5. Do you understand? Now, if they state the maximum value and at what x value that occurs, then you do state both. But if it says maximum value, the max is 5. That's it. That is the answer to that question.
you don't always need to put the where it happens.
No, sometimes you don't
Okay.
care. Okay. So it's really about like, what's the question asking, right? And this is why I don't take this as an answer for that, because it doesn't tell me how to answer the question, right? You could say, well, I'm getting it from this, right? But this is the max value. This is where it occurs. But a lot of times, like somebody asks you, how high did that ball go? Right? Maybe that's all you care about. Maybe you don't care about how long it took to get there. Do you know what I'm saying? Maybe all you care about is the height. Okay. So,
Yeah, that makes sense.
yeah, it's just a matter of what do you care about. All right. So if we go to, I'm going to do number 9. Okay. Okay. This, if I'm not mistaken, f of x is equal to x squared minus 6x. Is that what it says?
Yeah.
Yeah, I don't have my book open now. Oh, but I will if I have it. Hold on a minute here. I'm going to bring it up here. I can actually look at it while hold on a minute. Let's set this up so I can see the problems as we're going through it. There we go. All right, it says express the quadratic in standard form. And standard form now is
A
yeah.
times x minus h squared plus k.
That's right. So what I would do is, if this is the function, right? If you notice, to complete the square, I would have to do x. What do I do?
Divide the 6 by 2, which
Yep,
gives us -3. Put the
yep,
square and then
right.
square the new term.
So I've added 9, and in order to balance it back out, I'd have to subtract 9. Do you see? This is the original function. I can't have a number. So this is a weird one because it's 0, right? So here's how it works. If I've added 9, adding the 9 creates this. Do you see that? But I've added 9, so I have to subtract 9. And this is my standard form. Okay? Does that make sense? And I am recording
Yeah,
this, by
I
the way.
just
You
needed to
can go
take a
back
photo
to it.
so I could look
Yep.
over it later.
Okay, so that's the same thing. All right. Okay, so once I have it in this form, the book says find its vertex and its x and y intercepts. Well, the vertex is easy. What's the vertex?
3 and -9.
Here it is. Okay. How would I find the x and the y intercepts?
You just look at the vertex. The x-intercept
That's not going to give me
is
that's not going to give me the intercepts. I'm going to tell you right now, there's a super easy way to get the y-intercept.
set
So
x equal to 0.
yeah, and go back to your original function. Don't even look at this because you'd have to solve. Go back to the original, which was this. If x is equal to 0, what would y be?
0.
Yeah. So the y-intercept is equal to 0. What's the x-intercept?
Also 0
Yeah, because it
because,
goes through 0, 0.
yeah,
Exactly.
I was
Yeah.
panicking. I was like, something doesn't seem right here.
Okay. All right. But I do mention the quote C term of the original function is always the y-intercept, because that's like getting rid of all of your x's, right? Okay. So and then if you were to graph this, you would do your so if you notice, this tells us exactly how to graph it, right? I think you've got transformations under your belt. What you know is first you start with the vertex, right? 1, 2, 3, and -9. Ooh, that's going to be, let's just call that -9. And what I always kind of do, you want to think of this as this is your line of symmetry, right? Okay. So you have like this little line of symmetry, and you to graph it, what you can do is you obviously you're going to plot the vertex, but then you can do what we call square stepping, right? Um, Now this one, if I do know that I have this point, right? I would always plot the y-intercept, which means if I have a point here, I have a point here, right? Symmetry, right? Here's my
Yeah.
+3, here's my -3. So if I want one more, it's not real. I don't have to plug in a table. Notice this is an A, the A is 1. There is no vertical stretch. So it's just over 1, up 1, over 2, up 4, right? And so you could just plot a few of these and go this way. And then, of course, you have the symmetrical points going this way. Okay? This is what we call square stepping. You've done this with linear equations, right? If you know the slope, you go over, if the slope is
I
up 3
remember
over
you
1,
talked about it,
yeah,
but I was pretty lost the first
yeah.
time.
But this is so easy to graph. So notice, I know where the vertex is, right? If this is a factor of 1, then it grows by 1 times the squares. So if I go over 1, if x goes over 1, I'm going to go up 1. Or if x goes back 1, because 1 squared is still going to be a 1, right? So in other words, I'm going to put in an x, then I'm going to grow the function by the square of whatever x is. So if I put in if I go back 2, I'm going to grow by 4, and so on. If I go back 3, I'm going to grow by 9. Do you see how that works? Right?
Yeah.
This is 3, and I'm going to have to go up 9 to get to the next point, the square of 3. So graphing these, you can just graph by what we call square stepping, okay? Stepping it up by squares, all right? And let's just do one more that might be a little bit more complicated. Let me do one, like number 15. Okay. The f of x is equal to, this one has a negative. Okay. So if I want to turn this into the standard form by completing the square, right? I kind of want to, this is my original function. I think what I would prefer to do is pull that negative out. It's not really fun to complete the square with that negative. So I actually could think of this as -1 times x squared minus 6x,
Wait,
right?
why wouldn't you just do negative x times x minus 6?
It'll be the same place, but when you're completing the square, throwing those negatives in there really mess you up. Trust me on this particular thing. Notice what I'm doing here. I'm just rewriting these two terms here. I'm rewriting them with the negative out because to complete the square, I only want to work with this. Does that make sense?
Yeah, I think so.
Okay. So I'm going to keep going. I'm going to keep my -1. This is going to be my x minus 3, the quantity squared, right? And if I do that, what do I need to add to complete the
Subtract
square?
9.
Okay, so eventually I'm going to complete the square in here. Does that make sense? But you're right, I have subtracted 9. Make sure you're understanding that this is tricky here, okay? So I'm just
Yeah,
I'm
I
making
see
this
it.
equal
It's
to
just
this.
complicated.
With a negative, you just have to be careful. It's so easy to make a mistake with negatives. But this is that point where we went through in chapter 1, that what did I just add? I added a -9, therefore I have to add 9. Okay? Do you see that?
Wait, now I'm confused.
Okay, watch. This is so this is to complete the square, right? X minus 3 squared, the quantity squared, is equal to x squared minus 6x plus 9. This is equal to this, right? But what I did is I had to add 9 to complete the square. But notice the outside function is I'm multiplying that 9 by a -1. So what I really did is even though I added 9, I really subtracted 9 from the whole function. That's the effect of completing the square.
Which is why you then added 9.
Right.
Okay.
So if I think about it, I subtracted 9, I have to add 9. If this was positive, if I added 9, I'd subtract 9. But this is making it negative, right? Okay. So because I added 9 here, I have to add, this, right? Add 13. Okay. You do want to slow down on these. Okay. When I have anything other than, I think I have a video link in there that also works some more of these if A is negative or is something other than a 1. But now this is the function this is in the vertex form, now called the standard form in calculus, right? Okay. So important that they call it the standard form. So what does this tell me? And actually, you know how you can check it? You could if you plug this in and if you plug the original function in, they should graph exactly the same parabola. You can check it in Desmos or your graphing calculator. They're algebraic rearrangements of each other. So this and this should graph exactly the same parabola. Okay? So what is the vertex? What is the vertex here?
Uh, 3 and 13.
313. Okay. What's it going to look like? Let's think about
An
the transformation.
upside down
Yep.
parabola.
So this is upside down, and the vertex has been shifted right 3
3.
units and up 13 units, right? And that's why you have the vertex at 313, okay? Yeah, that's it. So if you were to graph this, graphing's not that hard. Let's take a moment. Let's actually do that right now.
Would the y-intercept be 13?
Yes. No, I'm sorry, no. Go back to the original function.
Wait, the y-intercept is 4.
Yes, the y-intercept is 4. 1, 2, 3, 4. So the y-intercept will be there. You could always plot that first if you want to. There it is. If x is 0, they all go away, right? And then the line of symmetry is x equals 3, right? So it's about here. Okay. Could have made that a different color, I realize. Let's do that. Okay, so if this is x equals 3, this is my line of symmetry. My vertex is over 3 up 13. So let's just call that 13. Okay, so there's the vertex. It's a down, down. So if I have this, which is over 3, then I've got another point over here, right? And then I could look for, again, I could go, the stretch factor is just 1. There's no stretch. So I should be able to graph this by going over 1, down 1, right? Over 2, down 4, right? And so on. So I would get a nice sketch. I do look at the roots and think, do I have any integer roots? Well, 13 is not a perfect square, so I'm not going to get an integer root. Do you understand? So I'm just going to sketch through, right? And just that would be my graph.
So an integer root means like it's not going to be a 0 on the x-axis.
Well, there's a 0, but it's going to be an irrational number. So you actually, you are going to be very often required to figure out what these are. And it's much easier to figure this out from this form than it is from this one, because this one won't factor. So for this one, if I want to get zeros, if all I care about are zeros, my only option here would be to complete the square or to use the quadratic formula. When I complete the square, I get all this other information. That's why I'm a fan of it, right? Not to mention you have to know how to do it to do other things, but notice it's
You
not
can
hard to
set
get
this
zeros.
equal to 0.
Right, you set the whole thing equal to 0. So I'd say that 0 is equal to -1 times x. Don't do anything to the square until you get it by itself, right? Plus 13. So the 0 here, notice I could move plus 13 over here, and I get -13.
X is equal to 3 plus or minus the square root of 13.
Exactly. Right. I'm going to get x minus 3 is equal to plus or minus the square root of 13. And if I want x equals, I'm going to add the 3 to both sides. And
And
there it
then
is.
that's when you get your zeros or
Exactly.
solutions or roots.
And let's think about this. Estimate this. The square root of 13 should be a little closer to 4 than to
Then
3,
5.
right? Huh?
I said it
So
should be a little closer to 4 than 5, right?
3. It's in between 9 and 16. Square root of 13.
Oh, right. I
Right.
forgot the
Yes,
square root
right.
of 4.
So it's going to be around, let's just say around 3.5, right? So the roots should be around about 3 plus 3.5, right? About 6.5. I don't know why I have a 7 there, because I'm in my head, I'm doubling the 3.5. Should be about 6.5 or minus the 3.5. So it should be about -0.5. So if you graph this on Desmos or on your graphing calculator, these two values, this one should be about right about there. You can estimate them and know you're about there, right? Okay. All right. So they should be awfully close to that. Notice my sketch even is really close to that. Okay.
Yeah.
All right. So that is that. Let me see if there's any, that's a hard one because that, like I said, with that negative there, pretty much done everything there that you're supposed to be doing. Something like number 25.
The rest of them seem pretty easy
Yeah,
after.
number 20. Yeah, after this, number 25 is one that has a constant. And you do recognize this. We did work on this in chapter 1, so it's not completely right. So this one here, if I want to get this in standard form, what's the first thing I do?
Pull out the 3.
Yeah. And it's only out of the A and the B terms. And I leave myself a little room for my completing the square. Leave this out, right? Because it's going to you get a fraction and you don't really want to deal with that. So now I'm going to get is equal to 3 times
X minus 1.
quantity squared, right? And here's
And
where
we
I have to
added a
be
1 in the
careful.
first function.
Add the square of -1, which will be a +1. But what did I just add?
3, so you want to subtract 3.
Yep. So to complete this, 1 minus 3, I get -2. There it is. Yeah. And the more you do it, the easier it gets, right? Okay. So the vertex of this one would be,
1, -2.
there it is, right? Okay. And then again, this is going to be your y-intercept. If you want your zeros, you would just set this equal to 0, which would give you, this would be equals 2 positive. You'd divide by 3 to get this. You end up with x minus 1 is equal to plus or minus the square root of 2/3. Unless you have
Wouldn't that just be √5/3?
root 5. Where do you get the 5 from?
√6/3.
Root 6.
Because you have a
Oh, yeah.
rational under the.
If you rationalize it, yeah. In other words, exactly. Because if you did this, you create your perfect square. Yeah. And you will, for a final answer, you'd have to say x is equal to 1 plus or minus the square root of 6/3.
I
Of course,
keep accidentally adding my rationals instead of multiplying them.
okay.
Like rationals throw me off sometimes.
Yeah, you're good at radicals, you mean? Yeah, you're gonna work with them so much, you get better and faster at them. The point I was gonna make is actually we'll use this to kind of estimate it, right? So this won't even be a 1. So it's really 1 plus a little less than 1, or 1 minus, actually more like a half, right? If the square root of 2/3, I don't know what that is. It's gonna be less than 1, right? Okay. Or is it more than 1? Now that I think about it. The square root, let's say 1/16 would be 1/8. Yeah, it's bigger than 1. It'll be a little more than 1 is what it would be. The other way around, right? Because the fractions are backwards. If you square a fraction, right, you get a smaller number versus a bigger number. And if you take the square root, you get a bigger number rather than a smaller one. So this will be 1 plus a little bit, more than 1, and so on. Okay. So that's pretty much when it comes to when the applications. If you have something like number 35, this is where your graphing calculators, or I would use -b/2a for this one. So my function, this is, I believe, I can't remember. I think this is a number 35. What's it telling you? It just says, yeah,
-7t
yeah.
squared
It doesn't
minus
tell you what it
49.
is. Whatever it is, the function is that t always means time.
It's a
So
parabola.
yeah, it is. It's an upside down parabola, right? So, I mean, this is similar to a projectile motion. Just projectile motion would be, what would happen with projectile motion, you're going to get a negative, depends on whether it's meters or feet. It would be -16 t squared if it was feet. And then if you give it upward velocity, like shove it up with a force of, say, 32 feet per second, and then let's just say you start at 5 feet in the air, that's what this function would be, right? So this is going to be something similar. Okay. And if all I care about, I believe they said, is how high, what would be the maximum? Okay, find the max or the min. That's all they're asking. Well, this is where I have my options. The main thing is I could say, well, the maximum or the minimum is, we're going to, x is equal to -b/2a, right?
Miss Julie,
Yeah,
why can't we just take the y-intercept here, because that's probably.
it's not. So watch.
Oh, because x
That's,
equals. Never mind.
so here's the thing. It'd be like, this is where it starts, but that's not going to be where the parabola, like, it's going to say it starts here, right? But let's see,
Yeah, that makes
down,
sense.
down, right? You're going to have something along the lines of that, right? Okay. So, let me, I'm going to use the -b/2a. So in other words, -b is 49. Twice A would be negative 14. Of course, 7 goes into both of these, right? This is 7 times 7. This is 7 times 2. So you get negative 7 halves or negative 3.5, right? Then you plug that back in. Usually you're going to use a calculator. I really don't usually do this by hand, but you'd say
Do you want me
negative
to use a
7
calculator?
if you want to. Yeah, I would use a calculator for this. I would use the decimal rather than fractions. Minus, oh, this is the square, minus 49 times negative 3.5. And actually, if you do this, you could cross these both out, plus 100. Okay. So I'll give you the y value. And you should get, if you did your calculator work right, 185.7.
I am on vacation right now and I kind of forgot my calculator, so
Okay,
that
if you
looks
plug
about
this
right.
into a calculator, you get that. Now, there is this weird property that you don't actually see very often in books, but it is kind of nice to remember. Remember, I told you if you know the quadratic formula, right? If you know the quadratic formula, it says x equals negative b, I'm going to call this 2a, plus or minus the square root of b squared minus 4ac over 2a. There's this really strange property. You have to really think hard about it as to why it works, okay? But what you can do is if you take the part that's whatever's under the root, if you were using the quadratic formula, let's just say to find roots, and if it's something like this, it would be like, where did the function start and where did it land, like on the ground. But if you take this, make it negative, and then you take this and you double it. If you're doing the quadratic formula anyway, this gives you the y coordinate of your vertex. This is your max or your min. The max or the min is going to be 4ac minus b squared. That's making this negative over 4a, which is really weird thing happens if you bunny ear this. You actually get c, right? That would be this, minus b squared over 4a. So it's a little formula. There is a formula for the y coordinate if you had the original. So what's cool is that if you know that the y value is going to be equal to this. I don't memorize this little formula because I'm so used to using the quadratic formula. Make it negative, double the denominator, but you could just do this, say I'm going to see it's going to equal c minus, take b squared, divide by 4a. That's going to give me my y value. And notice it does work. Okay, it's kind of bizarre. But if I take c, that's 100. And then I subtract b squared is 49 over 4 times, whoops, b squared. There it is, 49 squared over 4 times 7, that'd be 2 times 14. That would be what, 28?
Yeah.
Okay. And I could think of this is 7 times, yeah. I mean, this is going to end up being, this is going to be 100 plus my 85.7. I'm going to get the same number. I'm going to get 185.7. It's a little bit easier than finding this and then plugging it in, okay? So it's kind of a nice thing to know. And again, that usually comes out. Let's just say that I was asked to find at what time would this object, if it's projectile motion, at what time would this object hit the ground? Well, I would be plugging this into the quadratic formula. There's no way I'd complete the square with this, right? I wouldn't even attempt to factor. So in this one, I would say, well, x equals negative b over twice a, right? Plus or minus the square root of b squared because I could just say 49 because negative 49 squared is the same as positive 49, right?
Yeah.
B squared minus 4AC, right? Over twice A, I'd get negative 14. Notice I could actually take it with my calculator. I could take this, what's under my, so this would give me my roots, right? But it also gives me the vertex is the point, because this would be the x coordinate of the vertex. If I took this, what's under the root, made it negative, and took this and doubled it, I have the y coordinate, okay? So just little tips and tricks. I'm going to work with this again in class on Monday. I have in my notes, I have this, but for now, just make sure you're understanding that, the kind of the gold standard, you do need to know this, that's going to give me my line of symmetry, right? Which is where the vertex is going to occur. You're going to use this a lot. Okay. And
Yeah.
if I look at number 39, that one's actually even easier because the numbers are really nice. If you look at number 39, the numbers are not hard at all. If I have the h of x, even with the fractions, they're really not that bad. If for what I'm trying to do, right? If you're asked for just the max or the min, well, x is equal to negative b over twice a, right? So it's just equal to negative 2, right? To get the maximum, what I want is just I want the h of negative 2. That means plug the negative 2 in, and notice it's not going to be hard to do this without a calculator. 1/2 times 4
Negative
minus
6.
4,
I think the answer is negative
It's going
6.
to be, is it?
Wait, negative 8.
2, it's going to be 2 minus 10, negative 8, right? Negative 8, there you go. Yeah, so that's finding it, right? Using this and just plugging this into the function. A lot of them are going to be this easy. This one you didn't need a calculator for, right? Okay. So that's that's the main idea. If you know all of this, if you get pretty comfortable with this, as we did a lot of factoring in chapter 1. So like it's all about like if you think about the kind of the decision tree, like what am I looking for, right? What am I asked for? Well, wow. If I'm asked for, say, roots, solutions, right? Zeros or x-intercepts, any of those, right? That's where I'm going to factor. You set these, that means set equal to 0, right? I'm going to factor if I can, right? If I can't, what's my second option that I should consider?
Completing the square?
Yeah, I'd complete the square. That's basically if I have nice numbers, if the numbers aren't too hard, right? But if you look at something like that, negative 749, if your numbers are big or you've got decimals, you wouldn't. I would say this if it's convenient, because if you complete the square, you easily get the vertex as well. You get a lot of information from that. If neither of these work, last resort, use the quadratic formula. But just remember, with the quadratic formula, you can still get the vertex, which means you can still get the max or the min, right?
Vertex form?
Pardon?
Vertex form just always seems like the best one to go with if
It is
possible.
there's a reason they call it standard form in calculus, because it is considered the most convenient. But let's just say you just want the solutions. You're just algebraically solving for the solutions, and you have decimally numbers. Completing the square with gnarly looking decimals is not fun, right? So there's just going to be sometimes we're going to completely bypass that. You'll know when it's going to make sense to use the quadratic formula. And you still get the vertex with your x equals negative b over 2a, and your y is going to equal, well, you're going to take your b squared minus 4ac, you're going to make it negative, and then you're going to double the denominator. That'll give you the y coordinate of the vertex, okay? So that's if you're doing root solutions or now, if you're asked for a max or a min, right? If they ask you for that, well, again, you're looking for the vertex. So what's the best way to get the vertex? Believe it or not, if you could factor, the line of symmetry is going to be right in the middle. Sometimes you could figure that out, but it is going to be negative b over 2a and then plug in, right? It's the max or the min. Another way to look at this is going to equal the f of negative b over 2a. Does that make sense? You're going to find this
Yeah.
and plug it into the function, right? Or you could use this little, formula. But this is kind of the gold standard to know that. So it's kind of like, which are we being asked? Are we asked for root solutions? We have to do these. We focused on this in chapter 1. Right now, because we're doing a lot with functions, they're asking you what's the max or the min. Now there's more focus on max or min, but in calculus, they're equally as important. They're both crucial to understanding calculus. Okay. So I think that's good enough for
Makes
today.
sense to
And
me.